Hi everyone, in this week's video we will learn about backpropagation, an important algorithm used to train deep neural network. We will delve into an example neural network that is simple if fully connected, and we'll develop the Backprop algorithm step by step. We'll first go through a quick refresher on the components of neural network. Then we will review gradient descent, an algorithm which is used to improve neural network in a stepwise manner. Finally, we will delve into backpropagation, which is able to find our gradient that we need for the gradient descent algorithm. So let's get started. Neural networks are a collection of many moving parts which collectively make a classifier that is better than the sum of its constituents. So, for instance, we have the input layer, which is simply holding the input. It doesn't really exist, but it's a nice abstraction. We have the output neurons, output prediction in the right format, depending if it's a classification, a regression, or else. We have the hidden layer neurons, which are modeling the learning task. We have the weights, tying everything in on each connection, which are weighting each neuron linear regression properly. Finally, we have nonlinearity, which are called activation function, where the result of each neuron regression is fed to improve the learning. They come in many shapes. Here we have the logistic function. We can have ReLU, we can have tanh, we can have a leaky ReLU. There's thousands of them. They all have different properties. In our case right now, their derivative is what is of interest to us. The weights are what is important in a neural network. When fully trained, they are what is holding the learning. An algorithm that is used to train many machine learning classifiers iteratively is gradient descent. For more in-depth explanation with the Python implementation, you can take a look at my linked video. In short, what we do is use the error in the output along with a gradient of the loss function to iteratively modify the weights. In the case of a single neuron, it's as simple to implement as the error and the weights are directly related. However, in the case of a deep neural network, it is less obvious what the contribution of each weight to the final error is. This is where backpropagation comes in to get those gradients. The figure, along with most of the explanation, come from this wonderful tutorial by Matt Mazur, which I recommend everyone to take a look and to follow. The link is in the description. We will now derive what each of the gradients are on this fully connected feed-forward neural network. It's a simple network, however, it will give you a good idea of what steps are required to get the gradients. The first step before backpropagation is the forward pass, which is simple to calculate and code. If you want to take a look at an implementation, I also have a Python video on that. The backward pass is what happened directly after the forward pass and is the topic of today. After the forward pass, if we're in the testing mode, we have prediction. If we're in training mode, we have error. The error is what we will backpropagate throughout the network to modify the weights. So in this case, we have E total equal E01 plus E02. We will now take a look at the first weight that we can modify, W5 in our case. It's the weight directly attached to one of the output. So we want to find the gradient that represents the participation of W5 on the total error. This is the partial derivative of E total on W5. We cannot calculate this directly, so we need to go through some calculus with a chain rule to find components that we can calculate, which will build up to that gradient. So if we fast forward, once we get that gradient, we can directly apply gradient descent and we're good to go. If we zoom in on the environment around W5, we have the following. We have the total error, the partial error, which is half the squared error. We have the output of the nonlinearity. Here we're going to use a logistic regression, but we can use anything here. We have the output of the linear regression, so net, and then we have finally the output of the hidden neuron, H1, where the weights W5 sit. So let's look at the derivative of E total on out1, so the output of the nonlinearity. At this point of the tutorial, we will do a bunch of derivative, so brace yourself. So if we look at the error loss that we choose, we're gonna have we have a sum of the two half squared error. Here we're using the half because it will simplify the math. And if we take the partial derivative of e total over here, we're gonna have the equation at the bottom where only the first half of the addition is non-zero. If we simplify the formula, we get this, which can be rewritten as out O1 minus the target O1. This is the equation for that part of the gradient. And that's it. It's as simple as this. So one down, two more to go. Let's look at the partial derivative of the nonlinearity over the output of the linear regressor. So here the out O1, so the output of the nonlinearity, over the net O1, which is the output of the linear regression. So this is where the choice of the activation function will matter, as it will change the derivative we will get. So in our case we have the logistic function, so this is what the derivative look like. So the function has this form at the top, and if we calculate the partial derivative on net O1, we're gonna get the equation at the bottom, which is simple enough. So that's it. Two down, one more to go. Like I said, it's a lot of just calculus stuff. So now we will look, we'll try to find the partial derivative of the output of the linear regressor on W5. So the formula for net O1 is the following. So it's a really a simple line. If we take the partial derivative on W5, a lot of the variable in this line get removed, and we are left with simply out H1, so the output of the first hidden neuron. So that's it for W5. So we now have our three components which we can multiply together. That gives us this formula, which, if you pay careful attention, is just a multiplication of the subpart that we found separately. So we can then use that gradient for the update. However, I think to note here, only at the end of the propagation we're gonna overwrite W5, because some of the other weight update might need W5. So that's it. We now have found our new W5. The process is the same for W6, W7, and W8, everything in this layer. We will go in a similar process to find W1, the weight that is linking the first input to H1. If we look at the resulting chain rule, we have the following three components here that we'll demystify in a bit. So let's zoom in on the environment around W1. So those three components are actually 5, as the first one depend on the sum of EO1 and EO2. If we had more output, we will have more component in this higher order component. So let's look at the partial derivative of E total on the output of the nonlinearity of H1. So we have the following formula for the first component, which we can actually directly calculate, as we both derived them previously when we're doing W5. If we recycle the value that we found, we can straight away find the partial that partial derivative. For the other part, we can go into a similar process as we went for W5 with the other weights, which we will have to do anyway if we derivate W6, W7, W8. Find the other half of the partial derivative of E total on the output of H1. So it's really important to save all of those subcomponents when doing the backpropagation. This is why it's called a backpropagation, because we're gonna need those values as we go down the neural network. We can then sum up these two components and we have 1/3 of the job done. If we now look at the partial derivative of out H1 over the net H1, we get a similar looking partial derivative that we had before. If we use a different activation function here for this particular neuron, we will have a different formula over here. So this is directly gotten, and we have another part done. So the last partial derivative is similar than before again. The part that survived the partial derivative here is only the input 1. And we are done. We have our result for the partial derivative of E total for the weight 1. If we codify output, we just did to an arbitrary amount of output, right? we'll have this funny looking summation at the front that is multiplying the two other components that are trivial. So we can then calculate the updated W1 with a gradient descent right here. Now that we found W1, we can repeat it for W2, W3, and W4 using the exact same process. And we are done. This is the backpropagation algorithm. I will invite you to read entirely the Matt Azure blog post that I put in the description. We will go through a numerical example along with the explanation I just gave. So if you paid close attention, you will have realized that we need to calculate a lot of stuff by hand after we created our deep neural network architecture. The process will then be to hard code this neural network ourselves with a gradient afterward. If we wanted to have a big, huge neural network with super weird architecture, this whole process will be error prone and daunting. So this is where compute graph comes in with automatic differentiation. There's multiple way of automatically finding derivative in the compute graph, but that will be a story for another week. So I hope you enjoyed the tutorial. If you have any comment, request, or feedback, I will gladly take them. Have a good week.